In this video, we're going to talk about derivatives in science. So this video is just focused on basically examples of where derivatives get used in science. So as a reminder, if y equals f of x is a function, and we have x changing from x1 to x2, then the change in x, which we write as delta x, equals x2 minus x1, and then change in y is f of x sub 2 minus f of x sub 1. And then the difference quotient is delta y divided by delta x, which equals f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. And the derivative of y with respect to x is just the limit as delta x goes to 0 of this difference quotient. So this is all review. But the reason why I'm focusing on this is that our function f, which is equal to y, could be anything. And so anytime you have something that changes with respect to some other variable, you have this idea of a derivative. And this comes up often in various areas of science. Usually x is time, so usually time is changing, and the other function is related to time passing. So the first example that we are going to look at of this is an example from physics. And this is kind of where all of the ideas of derivatives originated from, was studying this setup. And so if s of t is the position of a particle moving along a straight line, then v of t, which equals the derivative of position, is the velocity of the particle at time t. So we've talked about this before. The velocity is just telling us basically how fast we are going in a certain direction. And then the instantaneous rate of change of velocity the instantaneous rate of change of velocity is called the acceleration. And it is denoted by a of t, which is just v prime of t, or the second derivative of the position function. So this is one example of where derivatives can be used. We're going to look at a concrete example and answer a bunch of questions about the situation. And so we're going to suppose the position of a particle moving along a straight line is given by s equals f of t is equal to t cubed minus 6t squared plus 9t. And so this is our position function. And we're just going to answer questions about this particle. So first we want to find the velocity at time t. So we want to figure out the velocity of this particle at time t. And so all that this is asking us to do is to take the derivative of the position function. And so the velocity time t is the derivative with respect to t of f of t, which is the derivative with respect to t of t cubed minus 6t squared plus 9t. And using the power rule, this equals 3t squared minus 12t plus 9. And so 3t squared minus 12t plus 9 is then the velocity of the particle. So this is telling us then the velocity at any given point in time. And to make that a bit more concrete, if we wanted to find the velocity of the particle after 2 seconds, this is just asking us to find v of 2. That's all the velocity of the particle after 2 seconds is, so we want v of 2. So we're just going to plug 2 into our derivative expression. So this gives us 3 times 4, which is 12, minus 24 plus 9. So plugging this all in, we end up with negative 3. Then I didn't write down the units, but everything's in meters per second, or in meters. And so S of t is measured in meters, just so we have units to talk about. And so this tells us that the velocity after 2 seconds is negative 3 meters per second, meaning that we are moving backwards at the 2-second mark at a speed of 3 meters per second. The negative is just telling us the direction we're going. So we're going backwards if we're negative. Next, we want to find when the particle is at rest. So a particle is said to be at rest when it has no movement, meaning it's not moving forwards or backwards. So this would be when v of t equals 0. So in other words, we want when v of t equals 0. So we're going to set our derivative, which is 3t squared minus 12t plus 9, equal to 0, and then we just want to solve this. So dividing everything by 3, we'd get t squared minus 4t plus 3 equals 0. And this is t minus 1 times t minus 3 equals 0. And the only way a product of two things can be 0 is if one of them is 0. And so that means that we're going to be at rest when t equals 1 or t equals 3. And so there are two places where we're at rest. When the particle is not moving, it's just standing still, essentially. And that's at 1 second and at 3 seconds. Next, we want to know when is the particle moving forward, or in other words, the positive direction. Okay, so we want to know when is our particle moving forward. As I mentioned a second ago, the sign of the velocity tells us if we're moving forwards or backwards. When velocity is positive, we're moving forwards. So we want to know when is v of t greater than 0. And so the way that we do this is we find when it's equal to 0. So you find when v of t equals 0, and then use a sign line, which I will do this in a second, to determine the sign over each interval. And so the idea here is, by the intermediate value theorem, which we covered in a previous video, we have to hit 0 to change signs. So the places where it's 0 is where it could possibly change signs, but outside of those places, the velocity is going to be forced to either be positive or negative for the entire interval. And so what a sign line is we set up an interval in which we list the points that we care about, which are the points where we are 0. And so we will 0 at 1 and 3. That's what we found in part C. And now on the whole interval from 0 to 1, the sign has to be either positive or negative, because we're 0 at 1. And then from 1 to 3, the sign has to be either positive or negative. It can't change in the middle. And so we just have each of these places where it's going to either be all positive or all negative on the interval. So from 0 to 1 is our first interval, from 1 to 3 is the second interval, and from 3 to infinity is the third interval. So we can only change signs at 1 and 3, because that's where we get 0. And now what we do is we just pick a value to plug in from each of these intervals. We call it a test point usually, and we see is the velocity positive or negative there. And so remember that the velocity function is 3t squared minus 12t plus 9, which is 3 times t minus 1 times t minus 3. It's a little easier to plug it into in that form. And so first off, if we check v of 0, because 0 is in our first interval, we'd get out 9, which is positive. So that means we're positive on the whole interval from 0 to 1. And we don't include 1 because we know we're 0 at 1. Now we check from 1 to 3, so I'm just going to plug in 2. So this would be 3 times 2 minus 1 times 2 minus 3. And if you can calculate this, you get to negative 9. So we're negative on the entire interval from 1 to 3. And then picking some value between 3 and infinity to plug in, I'll pick 4, so we have 3 times 4 minus 1 times 4 minus 3. So this is 3 times 3 times 1, which is positive 9. And so we're positive from 3 to infinity. And so what this then tells us is that we are moving in the forward direction on all the intervals where we had a positive velocity, which would be 0 to 1, union 3 to infinity. And I didn't say this before, but we start at 0 because time starts at 0. You can't have negative time, negative seconds. So we just assume that time starts at 0. And then we're moving backward when the velocity is negative. And so it's negative on 1 to 3. And so we found both when we were moving positive and we were moving backward. So when we were moving forward was 0 to 1 and from 3 to infinity. And then backward was from 1 to 3. Okay. The next thing we want to do is we want to draw a diagram of the movement of the particle. Now, one thing to note here is what the particle is actually doing is I have some line here, and the particle is just moving along this line, and then it moves backwards along the same line. So you're just moving forwards and backwards on a line. I'm going to actually draw it as if it like curves, even though it's just moving on a straight line, just so we don't have these overlapping bits. And all I'm going to do to feel this out is use what we just did in part D. So I'm just going to use when we're going in the positive direction and the negative direction. And so we have at time t equals 0, you can plug in 0 to see that the position there is also 0, just plugging 0 into s of t. And so we start here at the place 0, and then from time t equals 0 to t equals 1, we're moving in the forwards direction. And so this would be t equals 1, which is when we're in the forward direction. And if you plug 1 into s, you see that you get 4 out. And then from 1 to 3, we know we're moving in the negative direction. So from 1 to 3, we're moving in the negative direction. Here, we'd have that t is 3. And if you plug 3 in, you find s is also 0. And then that's just using the whole 1 to 3, we're moving backwards. And then from 3 on, we're moving in the forwards direction. And so our graph looks something like this. It was moving in the positive direction from t equals 0 to 1. And then from 1 to 3, it's moving backwards. Then from 3 to infinity, it's moving forwards. So this just is kind of a diagram to show us how is this particle moving, which can be helpful in actually thinking through what's happening with this particle, rather than just having the overlapping paths. Next, we want to find the total distance traveled by the particle in the first 5 seconds. Okay, and so I'm going to use the diagram here to kind of explain what we're doing here. So say t equals 5 is somewhere over here. So what we want to then do is we want to know the length of this path from 0 to 5. So we want to know this entire path going both backwards and forwards. And so now if I just did s of 5 minus s of 0, then all I would be doing is taking this distance right here. That would be s of 5 minus s of 0. It's just that length right there. But notice I backtracked for some of the time. So from 1 to 3, I was going backwards. And that's not captured by this distance from 0 to 5 if I just do s of 5 minus s of 0. That's just capturing the total kind of displacement is what it's called. It's how much we've changed from where we started. But we want the actual distance. So we have to consider when we're moving forwards and backwards as separate situations. And so we know we're moving forwards from 0 to 1. And so on 0 to 1, our distance traveled, it's still going to be f of 1, or I guess I've been calling it s. So it's still going to be s of 1 minus s of 0. So this is the distance we travel in that first second. And so plugging 1 into s, just as a reminder of what s is equal to t cubed minus 6t squared plus 9t. So if I plug 1 into this function, you get 1 minus 6 plus 9, so you get out 4. And then if you plug in 0, you get out 0. And so we move a distance of 4 meters on the interval from 0 to 1. Now I'm going to include 1 just for completion's sake. Right at 1, you're not really moving at all. Okay, so now we want to consider the interval from 1 to 3. Now on this interval from 1 to 3, we are moving backwards. And so I'm going to still write absolute values, so I'm going to do s of 3 minus s of 1. These absolute values take care of the fact we're going in the negative direction, and they'll turn the negative value we get positive. So s of 3, I said before, when you plug in 3 to s, you get 0. So we get 0 minus s of 1 we know is 4. So it's the absolute value of negative 4, which is positive 4. So we move 4 meters on that interval from 1 to 3. And we kind of saw that in our diagram, that from 0 to 1 we went from 0 to 4 distance-wise, then from 1 to 3 we went back to 0. And that's kind of modeled by what we just found with distances, that they would cancel out in the displacement form. Now from 3 to 5, we're going to do s of 5 minus s of 3. Plugging 5 into s, you get out 20. And then at 3, we already said you get out 0. So we move 20 meters in the time from 3 to 5. And now the total distance is just the sum of these. And so in the first 5 seconds, we move a total of 28 meters. We just do 20 plus 4 plus 4. And so that's how far we move in those 5 seconds, distance-wise. And so we're not just counting the overall place we changed from 0 to 5, we're finding the whole length of that curve from 0 to 5. And so next we have part G. So in part G, we want to find the acceleration of the particle. at time t. Now remember, acceleration is the derivative of the velocity, and our velocity function is 3t squared minus 12t plus 9. So the acceleration is the derivative of velocity. And the derivative of the velocity is just 6t minus 12. And so our acceleration is given by 6t minus 12, which this is telling us the instantaneous rate of change of the velocity. Next, we want to figure out when is the particle speeding up and slowing down. Well, instead of saying or, I'm going to say speeding up and slowing down. So this is kind of two parts. And so we're speeding up if we're going in a direction and we're going faster in that direction. And so the velocity tells us our direction. And so when v of t is greater than 0, we would be speeding up if we are getting even larger positive numbers out, meaning that the rate of change of the velocity is positive. So when v of t is greater than 0 and a of t is greater than 0, we are speeding up. So a way to think of this is if you have a car that you're driving forwards and you have an acceleration that's positive, that means the car is getting faster going forwards, so the speed of the car is getting greater. And so you're speeding up. Now we want to consider when the velocity is negative. So if the velocity is negative, this means we're moving backwards. So you can think of it kind of like we have the reverse in the car going on the long road. So we're moving backwards along the road. Well now, if the acceleration was positive here, that means that despite velocity being negative, it's getting bigger in value. But getting bigger in value means it's getting closer to 0 because it was already negative. And so that would actually be slowing down. Well, speeding up is if acceleration is also negative, meaning that we're going backwards and we're getting more negative. And so, in a sense, we're getting faster going backwards. And so, if the acceleration is negative, we are also speeding up. And again, this is just coming from this idea that the acceleration sign is corresponding to velocities getting larger in values or smaller in values, but the velocity tells us our direction. So when the velocity is negative, we actually want a negative acceleration to be getting more negative numbers. So in the absolute value, we're getting a faster speed that we're going. To summarize this, if v of t and a of t have the same sign, we are speeding up. And if v of t and a of t have opposite signs, we are slowing down. And so this just comes to checking the signs that we have. And so as a reminder, we already did when v of t was positive. V of t is positive from 0 to 1, union 3 to infinity. And then a of t, this is when v of t is greater than 0. And v of t is less than 0 on 1 to 3. Now we want to do the same thing for a of t. Now a of t, remember, was just equal to 6t minus 12. And so a of t will be greater than 0 when 6t minus 12 is greater than 0. So that's going to be when we're greater than 2. So from 2 to infinity, our acceleration is positive, and our acceleration is negative for everything before that. So from 0 to 2, our acceleration is negative. At 2, it's 0. And so now we just compare to figure out when we're speeding up and slowing down. We need the signs to be the same to be speeding up, and opposite to be slowing down. Now the way I do this is I work my way from left to right, so I'm going to start with the time of 0 and go up until I change one of those signs. So from time 0 up to 1, velocity is positive. So our first interval is going to be 0 to 1, the velocity is positive on that whole interval. And acceleration is negative on that whole interval. So from 0 to 1, we'll be slowing down because the velocity is positive. The velocity is positive on 0 to 1, and acceleration is negative. Next, from 1 to 2, they're both negative. So from 1 to 2, that's part of this interval for velocity, so it's negative. And so from 1 to 2, we're also in accelerations being negative. So we're speeding up then from 1 to 2. Now from 2 to 3, we're once again in velocity's realm of negative, but acceleration is positive from 2 on. And so we're going to be having opposite signs. So from 2 to 3, we're going to be slowing down because velocity is negative, acceleration is positive. And now 3 is the last place where we change signs in either of them, and they're both positive from 3 on. And so from 3 to infinity, we are also speeding up. So we're speeding up on 1 to 2 and 3 to infinity, and slowing down on 0 to 1 and 2 to 3. And so this is just one example of where the derivative comes into play. And notice we were able to figure out a lot of different things. We answered 7 different questions in looking at this question, just of looking at derivatives of a particle moving. So now we want to look at another example of where derivatives come into play. And so if we let n equal f of t be the number of individuals in an animal population at time t. So we're just going to let f of t denote the number of animals in an animal population after time t. What we want to do is we want to figure out the growth rate. And so the growth rate can be found first in the average form. So the average growth rate, well, this is going to be the change in number of individuals, which will be f of t2 minus f of t1, divided by the time that elapsed, so t2 minus t1. So that's our average growth rate, but notice that's just a difference quotient. And so if we want the actual growth rate, or the instantaneous growth rate, we have that the growth rate, or instantaneous growth rate, is given by the derivative. And so we'd have the limit as delta t goes to 0 of delta n over delta t, which is just f prime of t. And so if we want to figure out the instantaneous growth rate of a population, we just take the derivative of the function that tells us the population size. And so this is another place where derivatives come into play. And so what we want to do is we're just going to answer the following question. So for a bacteria population, the size is given by f of t equals 2t to the t times 100 after t hours. And we want to find the growth rate after 4 hours. So we want to figure out how fast this population of bacteria is growing after 4 hours. And now what 2 to the t means is it's saying every hour the population is doubling. So we're doubling the size every 2 hours, and we want to figure out how fast is it growing after 4 hours. Now this really just amounts to figuring out the derivative at t equals 4. And so we need to know what f of t is, f prime of t is, I mean. So we're going to take the derivative with respect to t of 2 to the t times 100. And this is going to be equal to 100 times 2 to the t ln of t, ln of 2. So this is just using the fact the derivative of 2 to the t is 2 to the t ln of 2. And then we wanted it after 4 hours. And so f prime of 4 then is just going to be 100 times 2 to the 4th ln of 2, which is approximately 1,109 bacteria per hour. So what that tells us is after 4 hours, the rate that these bacteria are growing is about 1,109 bacteria per hour. And so that's just giving us an idea of how fast is our population growing. This is used often in biology to measure various ecosystems to see how fast things are growing and changing. Usually they also consider other things like predator-prey relationships, and that just ends up increasing the number of derivatives that are showing up and causes more complicated situations. But all of it comes down to these derivatives that are measuring the rate of change of the population. So now let's look at one more example. And so when we consider the blood, the flow of blood, through a blood vessel, such as a vein. So this is a vein or an artery. It is just a blood vessel. We model the blood vessel as a cylindrical tube with radius capital R. So that's saying that we have some situation like the following is what we're modeling. And the radius of this tube we're calling capital R. And so that's what we're saying a blood vessel is being modeled by. And then with radius R, and then it's going to have and length L. The length of the blood vessel is relevant, and that's just this. It's just the length. It's just how long the tube is. Okay? So now the velocity of blood moving through a blood vessel is greater when it is near the center. So the closer to the center of the tube are, the faster it moves, and it slows down as you get closer to the walls of the vessel. Okay, so blood doesn't move through a blood vessel at the same speed. The closer to the center you are, the faster you're going, and then you get slower as you go towards the edges. And so if little r represents the distance the blood is from the center axis of the blood vessel, then the velocity in the blood vessel is given by V equals P divided by 4 eta, which is a Greek letter, times L, times r squared minus little r squared, where eta is the viscosity of the blood, and P is the pressure difference between the ends of the tube. Okay, so viscosity, which is represented by this Greek letter eta, that's essentially how thick is the blood. So blood has varying thicknesses. That's what eta is representing. And then P is the pressure difference between the ends of the tube. So your blood it varies based upon one end of a blood vessel to the other end, how much pressure there is at each end. And so now what we want to do is we want to figure out the rate of change of the velocity as you move further away from the center. So in other words, as little r gets bigger or smaller as you change how close you are to the center, we want to figure out how the velocity is changing. And so this is called the velocity gradient. Is the instant rate of change of the velocity of the blood with respect to how close to the center of the blood vessel the blood is. And so this is going to be dV over d little r. So we want to compute what is dV over d little r. And so we have what V is. V we have is P divided by 4 eta L times big R squared minus little r squared. And we want the derivative of this with respect to little r. Now, when we take this derivative, the only thing we're really considering changing is little r. So assuming the pressure is the same, we're assuming the viscosity of the blood is the same, we're assuming the length of the blood vessel is the same, and we're assuming the radius of the blood vessel is the same. And so P divided by 4 eta L, those are all constants. And so we can pull those out in front of the derivative. So we really just have the derivative of capital R squared minus little r squared. But capital R is a constant with respect to little r. So we're going to P divided by 4 eta L times the derivative. The derivative of capital R will be 0, as that is a constant. It's not changing. Minus the derivative of little r squared is 2r, because that is changing. So doing this, we get negative r times P divided by 2 eta L. And so this is a formula then that tells us that the rate of change as we move further away from the center of the blood vessel of how fast the blood is moving.